Welcome back to Learn Civil Easy. Today we begin a brand new subject, Design of RCC Structures. And we are starting right at the beginning with the simplest question in the whole subject. Why do we put steel inside concrete at all? By the end of this video, you will know the answer. You will know exactly where those bars go in any beam you meet, and you will know the two design philosophies that everything else in this subject is built on. Let us begin. Here is a plain concrete beam resting on two supports. Now let us put a load on it. As the beam bends, something important happens inside it. The top half is squeezed, it goes into compression, the bottom half is stretched, it goes into tension, and in between there is a line where the material is neither squeezed nor stretched. We call that the neutral axis. Now concrete is superb in compression, the top half is perfectly happy, but concrete is very weak in tension. So the bottom half begins to crack, and once it cracks, it can carry nothing at all. The beam fails suddenly with no warning. So how weak is concrete in tension? The code gives us a number, IS 456, clause 6.2.2, tells us the flexural strength of concrete, FCR, equals 0.7 times the square root of FCK. Let us put real grades into it. For M20, that is about 3.1 newtons per square millimeter. For M25, 3.5. For M30, 3.8. Now compare each of those with the compressive strength beside it. You will often hear that concrete's tensile strength is about 1/10 of its compressive strength. That is a useful rough idea, but by the code formula, it is closer to 13 to 16%. And notice something interesting. As the grade goes up, that percentage actually comes down. Concrete never gets good at tension, it just gets better at compression. So we give the concrete a partner. We place steel bars low down in the beam right where the concrete was being pulled apart. Now when the load comes on, the concrete takes the compression at the top and the steel takes the tension at the bottom. Each material does the job it is good at. Together they are called reinforced cement concrete or RCC. But why does this partnership work so well? Three reasons. First, bond. The cement paste grips the surface of the bar, and deformed bars have ribs that add a mechanical grip on top of that. So the steel and the concrete around it stretch together as one. Second, thermal compatibility. Steel expands at about 12 times 10 to the minus 6 per degree Celsius. Concrete is in the range of 6 to 12 depending on the aggregate used, close enough that a change in temperature does not tear them apart. And third, protection. The concrete around the bars keeps out oxygen and moisture, so the steel does not corrode and it shields the steel from fire. Let us cut through that beam and look at the section. This is the drawing you will redraw 100 times in this subject. So let us name every part at the bottom 3 bars. These are the main bars and they carry the tension. At the top 2 smaller bars, these are the hanger bars. Their main job is to hold the cage in shape, though they also act as compression steel. Wrapped around all of them is a closed loop called a stirrup. The stirrup resists shear and it holds the main bars in position while the concrete is being poured. Now the dimensions, the width of the beam is B. The total depth from top face to bottom face is capital D. But the dimension we actually design with is small d. The effective depth measured from the top compression face down to the center of the tension steel. And finally, the clear cover. The distance from the concrete surface to the nearest bar. Here is a trap worth remembering. The nearest bar is the stirrup, not the main bar. For mild exposure, IS 456, Table 16, asks for 20 millimeters of nominal cover on a beam. Now we come to the most important idea in this entire video. Everything you have just seen reduces to a single rule. Steel goes wherever the concrete is being pulled apart. That is it. That is the whole rule. If you understand that one sentence, you will never again have to memorize where the bars go. You will simply work it out. So let us apply it 3 times to the 3 beams you will meet in every exam. Case 1. The simply supported beam. Load on top, supported at both ends. It sags in the middle. Let us draw the bending moment diagram underneath. The whole span is sagging, positive throughout, and it is largest at mid-span. Now apply the rule. Where is the concrete being pulled apart? The beam is sagging, so the bottom fibers are stretching. The tension faces the bottom. So the main bars run along the bottom for the full span, and we hook them up at the ends to anchor them. Simple enough, and this is the case everybody remembers. Now watch what happens when we change the beam. Case 2, the cantilever, fixed at one end, free at the other. Put the load on and the free end drops. Now think carefully before I tell you which face is being pulled apart. The beam is curving downward at the free end, so the top fibers are being stretched and the bottom fibers are being squeezed. This is hogging, and the bending moment diagram sits above the baseline, largest at the fixed support. Apply the rule, the tension face is the top. So in a cantilever, the main steel goes at the top, and it must be anchored properly back into the support because that is exactly where the moment is greatest. Now, this is the single most missed multiple choice question in this whole chapter. Students see the words main reinforcement and answer bottom out of pure habit from the simply supported case. Do not do that. Ask the rule. Which face is being pulled? Case 3, the continuous beam, running over 3 supports. This one carries both cases at once. Look at the bending moment diagram. In the middle of each span, the beam sags, just like case 1. So we have sagging moment below the baseline, but directly over the middle support, the beam is being bent the other way. It hogs, so there, the moment flips sign and rises above the baseline. The 2 points where the curve crosses the baseline are called points of contraflexure. The moment is 0 there. Now apply the rule twice. At mid-span, the beam sags, so the bottom is in tension, main bars at the bottom. Over the support, the beam hogs, so the top is in tension, and we must provide extra top bars right there. In practice, we do 2 things. We add straight extra top bars over the support, and we crank some of the bottom bars upward as they approach the support, so they follow the moment. And here is your memory hook for the exam hall. Look at the 3 diagrams together. Wherever the moment diagram sits below its baseline, the steel sits at the bottom of the beam. Wherever the moment diagram rises above its baseline, the steel rises to the top. The steel simply follows the moment. 1 picture, 3 cases, nothing to memorize. Right, we understand the material. Now let us talk about what design actually means, because the syllabus splits it into 2 halves. Functional design asks, does this building work for the people inside it? Are the rooms the right size? Does the circulation make sense? Is there enough light and ventilation? Does it look good? That is largely the architect's world. Structural design asks a different question. Will it stand up safely and economically? Where does every load go? How big must each member be? How much steel does it need? And is the whole thing stable? That is our world as engineers. Both must be satisfied. A building that stands up beautifully but cannot be lived in has failed. And a building that is a joy to live in but falls down has failed far worse. So what does a structural designer actually do step by step? 5 stages. First, structural planning, deciding where the columns go, how the grid runs, how far the beams span. Second, calculation of loads, dead, imposed, wind, seismic. We will spend the whole of the next video on that. Third, analysis, working out the forces and moments in every member. Fourth, design, sizing the member and working out the steel. And fifth, detailing, deciding how the bars are actually bent, lapped and placed on site. Please do not treat that last step as an afterthought. A perfectly designed beam with wrongly detailed bars will still fail. And through all 5 stages, 4 objectives must be satisfied at the same time. Strength, so it does not collapse. Serviceability, so it does not sag or crack in normal use. Durability, so it lasts its design life. And economy, so we are not wasting material. One more idea from the planning stage, and the syllabus asks for it by name, why we prefer symmetrical planning. Look at these 2 plans. On the left, a symmetrical building. Its center of mass and its center of rigidity sit at the same point. When wind or an earthquake pushes it sideways, it simply moves sideways. On the right, an L-shaped building. Those 2 centers are now apart. The same push makes the building twist as well as move, and that twisting, that torsion, is what tears buildings apart in earthquakes. Symmetry buys us three more things as well. The analysis is simpler, members repeat so formwork and bar bending are cheaper, and IS 1893 specifically identifies irregular plans and penalizes them. Symmetry is not just an architectural preference, it is structural insurance. Now, the last big idea of this video, how we actually design. There have been two main philosophies and you need both. The older one is the working stress method. Its idea is simple and cautious. Assume that both concrete and steel stay perfectly elastic, stress proportional to strain right through the working life of the structure, then design so that the actual stress under the real everyday load never exceeds a permissible stress. And that permissible stress is just the ultimate strength divided by a factor of safety, about 3 for concrete, about 1.78 for steel. Because we are mixing two elastic materials, we need a way to compare them, and that is the modular ratio M equal to 280 divided by 3 sigma CBC. It tells us how many times stiffer steel is than concrete, so we can convert the steel into an equivalent area of concrete. And note one assumption that matters. Below the neutral axis, we assume the concrete carries no tension whatsoever. We simply ignore it. The method we actually use today is the limit state method. Start with the name. A limit state is any condition beyond which the structure stops doing the job it was built for. There are two families. The limit states of collapse, flexure, compression, shear, torsion, and bond. These are about the structure falling down. And the limit states of serviceability, deflection, cracking, vibration, durability. These are about the structure being unpleasant or unusable even while standing. Both families must be satisfied. And the design rule is one inequality. Design strength must be greater than or equal to design load effect. RD greater than or equal to SD. Design strength is the characteristic strength divided by a partial safety factor for the material, gamma m. And design load is the characteristic load multiplied by a partial safety factor for the load, gamma f. For materials, gamma m is 1.5 for concrete and 1.15 for steel. Concrete gets the bigger factor because concrete is the more variable material. Let us put the two side by side. Working stress is elastic and permissible stress based. Limit state is semi-probabilistic, built on limit states. Working stress assumes linear behavior throughout. Limit state allows the real non-linear behavior at failure. Working stress uses one single global factor of safety. Limit state uses separate partial factors, one on the loads, one on the materials. Working stress works with service loads. Limit state works with factored loads. Working stress gives conservative oversized sections. Limit state gives economical ones. And in the code itself, working stress now survives only in Annex B, while limit state is the main method in Section 5. Now, one exam point. If you are asked for the single biggest advantage of limit state, the answer is not it is more economical. The real answer is that it treats uncertainty in the load and uncertainty in the material separately. The economy is just a consequence of that. Finally, the books. You will hear these numbers all through the subject. So let us fix what each one is for. IS 456-2000 Plain and Reinforced Concrete Code of Practice. This is the main rule book. If you own one code, own this one. SP16 Design Aids for Reinforced Concrete. Charts and tables that turn long design calculations into a lookup. SP34 The Handbook on Concrete Reinforcement and Detailing. This is how bars are actually bent, lapped, and placed. IS 875 Design Loads in 5 parts. That is next video's subject. And IS 13920 Ductile Detailing of Reinforced Concrete Structures Subjected to Seismic Forces. Now, why do we need that last one separately? Because an ordinary IS 456 frame is designed for strength. In an earthquake, strength alone is not enough. The frame must also be able to bend and absorb energy without falling down. In one sentence, IS 456 keeps the building standing under load. IS 13920 keeps it standing after the shaking. Let us recap. 1. Concrete is strong in compression and weak in tension. Only about 13 to 16% as strong too, so we place steel on the tension face and it works because of bond matching thermal expansion and cover. 3. In a beam section, know your main bars, hanger bars, stirrups and the difference between capital D and small d. 4. And this is the one to carry with you. Steel goes wherever the concrete is being pulled apart. Bottom in a simply supported beam, top in a cantilever, bottom at mid-span and top over the supports in a continuous beam. 5. Design means functional and structural, and the structural designer works through 5 stages from planning to detailing, and 6. Working stress is the old elastic method, limit state, with its partial safety factors, is the method we use today. In the next video, we take the second stage of that process and go deep, loads on structures IS 875 and IS 1893. If this helped, do subscribe and join us on Telegram where the practice PDF for this topic is waiting. See you in the next one.